All right, picking up from the last video, we just ended up doing single displacement, so I do want to do one more example because this is the most difficult one to do. So let's try another example before we move on. And I will do more examples after this video, but let's go ahead and do and one more single displacement. First thing is I know is this is single displacement. Why? Element plus compound, single displacement. Potentially, will it go or will it not go? Am I gonna play? Am I not gonna play? Forget it. Gronk. I can't even say his name. Last year, okay? Make up your mind, Gronk. Make up your mind. And now he's gonna play. Tampa. Lead is going to try to kick out who? Lead is a metal. Going to try to kick out the metal. Try to kick out sodium. You look at your spiffy chart. You go ahead and you look. You look at your chart and you find sodium relatively high up. You find lead relatively far down. So can lead kick out sodium? No, it ain't spiffy enough. Not going to happen. Not going to happen. This is Brad Pitt and Angelina Jolie. Oh, they're not together anymore. I know it. And this is me. Okay, I want to dance with Angelina. This is Brad Pitt. I'm competing with Brad Pitt. Not going to happen. So this is not going to kick out sodium. So what happens in a case like that? If it can't kick it out, what do? You write NR. No reaction. Right? No reaction. Would not happen. Okay, so there was an example of one that would not happen. So I didn't show that to you last time. However, let's say that I had aluminum. Okay. And silver, aluminum and silver. Let's try this. Would this happen? One more practice. Would this happen? Go to your spiffy chart, look it up, find aluminum, pretty much in the middle. Find silver, pretty much on the bottom, not reactive. So can aluminum kick out silver? Yes. Yes, it can. Hi-ho. Right? Get it? Hi-ho, silver. Yeah, funny. So aluminum kicks out the silver. Hi-ho! 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 Yes, I know it. We know. Okay, now here's another example of what I wanted to do as well, because this, on this side, I'd have aluminum by itself. Is it, first thing you should ask yourself is it diatomic? And you go, is it one of the 777s? If it is, I need a 2 for a subscript. Nope, it's not. Aluminum is not a diatomic molecule. Well, it's silver. So here's what if something gets kicked out, you have to check and see if it's diatomic. Is it? Is silver one of the 777s? Is silver hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine? No. So it is not diatomic when by itself. Keep asking yourself that question when you see a single element. Okay, so we're good then, right? We're good then, right? No, no. Here, we're good because silver is a +1 and chlorine is a -1. Here, we're not good though. Silver, this is chlorine is a -1 and aluminum is a +3. So that is not good, not well written. We have to do it correctly. So check your chemistry. You have to check and make sure everything is written correctly. Crisscross the charges. I get aluminum chloride. Now I'm not balanced. Oh, we know I'm not balanced, okay? We know that. I was talking about me personally. The equation isn't balanced. 3, right here I have 3 chlorines, so I need 3 chlorines here. I'll put a 3 in front of the chlorine, but that means 3 silvers. So put a 3 there for the silver. All right, so 1 aluminum, 3 chlorines, 3 silvers, and 3 silvers, and we're good. So there's another example, a lot of examples so far, and again, we'll do more later, of single displacement. Okay, move on. Let's get to that fifth kind, who used to the 4th kind. The 5th kind of reaction is called a decomposition, a combustion. I'm a mess today. A combustion reaction. Now, there are 2 different kinds of combustion reactions. Combustion means you're reacting with oxygen. You're burning in the presence of oxygen. You can't combust something without good old oxygen. But the classic combustion, okay, what's called a classic combustion reaction, is a hydrocarbon and oxygen. A non-classic would be something else burning in oxygen, like magnesium burns in oxygen. And we've got a lab to do this week on that one, or maybe that's next week. Magnesium oxide combustion. Okay, that would be a combustion reaction because you react with oxygen, your combustion. But if you're a classic combustion, and that's the one we're going to work on here, classic combustion. classic combustion, here's what you've got. You ready? You have a hydrocarbon. What does that mean? That means carbon and hydrogen, hydrocarbon. Carbon's written first though. All right, so then I'm gonna put an X and a Y here. Well, why'd you do that? Why don't you put something down? I will in my example, but I put an X and a Y there because it can be a lot of things. You can put a 2 here and an 8 there. You can put a 1 here and a 4 here. You can put a 3 here and an 8 here. They can be variable. That's why I put variables up there. Hydrocarbons come in many, many shapes and sizes. And actually a hydrocarbon that's specifically called an alcohol, if we had an O on here, which alcohol burns, it does burn, it combusts. We put an O on here and we have a lot of different combinations. Many combinations of hydrocarbons. So this is the generic way of writing a hydrocarbon. Okay, CH with variable. Then we're combusting it. So that means you gotta have oxygen. You're combusting it. It burns in the presence of oxygen. No oxygen, no combustion. And then this is always gonna form. Classic combustion, carbon dioxide and water. So if you're combusting in the internal combustion automobile engine, if you're combusting your hydrocarbon, your gasoline or your diesel, then you're using oxygen. Okay, it's got to mix with oxygen. Back in the day, you had a carburetor which mixed the oxygen, and you have the gasoline comes in with a sparky plug, go boom, a controlled explosion happens, moves the piston, makes the wheels go round and round. Okay, the wheels in the bus. Remember, wheels in the bus go round and round, round and round, round and round. And what you're going to get coming out the tailpipe is carbon dioxide and water. Okay, that's it. That's pure, 100% unadulterated, perfect combustion. Now the problem is, I said perfect combustion. Perfect combustion when the automobile engine doesn't end up being perfect. You're taking in air. So we're not just combusting because you're taking in air. So it's not just oxygen in the air. There's a lot more nitrogen, isn't there? Yeah, you know that. You do. You know there's more nitrogen. So if it's just oxygen, we would get a perfect combustion reaction. But since there's nitrogen in the air, we get nitrogen compounds, which are actually the ones that cause smog. So that's why automobiles cause a lot of smog, because of the nitrogen compounds that are actually produced. We're sticking with pure, perfect combustion. Okay? It's easier. You might get into advanced chemistry later on at one point, and you'll get into more stuff. But for now, we'll do perfect classic combustion. All right, and there it is. That is actually the form. It's not like A's and B's here, because it's always the same compounds, the same elements. So there's no point in putting down A's and B's. That is the generic way of writing a classic combustion. Let's do an example. I actually did one of these for you in the balancing video, when we end up having to do with the half method of having a half on the side and doubling everything. Some of you might remember that if you watch that video. So here is a combustion reaction. This is the simplest combustion reaction because it's methane. So if you see this, CH4 and O2, you go boom. It's combustion, man. Classic combustion. I have a hydrocarbon and oxygen. I know every time it's going to make what? CO2 and water every single time. So I write that down. Then I go ahead and try and balance it. One carbon, four hydrogen, 1, 2, 3, 4 oxygen. Balance it. The oxygen are split here, so I have to be careful. Total of 4 on the right, total of 4 on the left. I am now nice and balanced. Okay, we could have what's called a combustion reaction, where you have a non-hydrocarbon, like I mentioned this earlier, and we are going to do this one in lab, so I'll go ahead and write this one down. Where you have magnesium, which burns readily in the presence of oxygen. It's very impressive. Good stuff. You like it. Magnesium burns with oxygen, and you get magnesium oxide. Now, some of you might say, that's a synthesis reaction. And you know what? You would be correct. We would actually be able to classify this, and this happens sometimes, as either a synthesis reaction or a combustion reaction, because you have the O2. Actually, if I were to classify it, I would prefer that you classify that as actually a synthesis reaction. Because when I refer to combustion reactions in this class, we're going to be talking about the classic combustion with hydrocarbons. All right, so if you said this in combustion, I go, yeah, okay, right, but do recognize that it is a synthesis reaction. You have the two elements coming together and forming that compound. All right, so, and there's an example. There's an example of a classic combustion. We'll just do one more here. Let's say that I've got some C2H. Now let's go C3, 1, 2, 3, 1, 2, 3, 4. 5, 6, 7, 8. C3H8. 1, 2, 3, 1, 2, 3, 4, 5. Yep, C3H8. And smoke 2. Predict the product. Predict the product. It's a hydrocarbon and oxygen. The product's the same every time. Every time. It's CO2 and water, and then what you have to do is go ahead and balance it. So 3 carbons, put a 3 here to balance the carbon. I look at the hydrogen next. There are 8 of them. So if I have 8 hydrogens, I want to put 4 here to get 8 hydrogens. Nice, balance the oxygen. 2 here. Ooh, look at this. 3 times 2 is 6 plus 4. So on this side there are 10, and then I need 10 over here, so I put the 5 there. And I did show you an example in balancing of a hydrocarbon reaction where this ended up being 7 on this side, and we needed 3.5 to balance it. Remember that? 3.5 times 2 is 7 is balanced, but you know you can't have a half. So you'd have to multiply everything by 2 to get rid of the fraction and keep the proper ratio. Okay, so that's a little bit of going back review and balancing, but just another example of a hydrocarbon. They're all done the same way. Not too bad. And by far and away, the most brain-teasing basic reaction type, it is going to be the single displacement reaction. Okay, so we'll keep this one video kind of short because the last one was really long. It was like, oh my God, you were just drooling and falling asleep as you were watching that. And after this, we'll pick up in the next video. We'll do some off of the sheet of reaction predictions and go and just do some examples for practice.